Hello, welcome back to Cracking the Cryptic, and today I'm going to be having a look at a puzzle that's been sent in to us by Eric Rathbun. I think it's a debut for Eric, so looking forward to this and seeing how it goes. But I do want to, certainly, I want to tell you about the forthcoming Patreon reward that is going to be not the monthly reward, but an extra bonus Christmas reward, the puzzle pyramid hunt that's been set by Spartacus, Peter Venus, and Panthera, and that is going to be fun. Lots of puzzles to have a go at there. Some of them Sudoku, some of them pencil puzzles, all of them magnificent. Simon and I have worked our way through it. It's brilliant. It's really good. Now, what is also very good is the current December monthly reward. The competition we're closing on the 20th. That is the Mexican standoff. Send in your answers. Loads of people have. It is pretty approachable. Actually, the puzzles aren't simple, but they're all doable, and that's quite good fun. There are places to chat on the Discord server if you're struggling, and people will help out because it is a very friendly community. Actually, I do want to say thank you very much. I was worrying yesterday about, I could tell I'd clearly missed a lot of bits of solving in the puzzle, but the comments were very kind and suggested that people are still benefiting. Even when they can see the thing I'm missing, they are still enjoying watching the video. So I'm grateful for that because it'll happen again today, that's for sure. So today's puzzle is called Ready, Set, Go, with set in capitals. The rules are these. Normal Sudoku rules apply. Digits cannot repeat within a cage and must sum to the digit in the top left corner if given. Digits along an arrow must sum to the digit in that arrow's circle, and digits cannot repeat along either of the diagonals. So these 4 cells must add up to 29. These 2 cells add up to the number in the arrow there. Bear in mind on this arrow, these 2 could be the same because that doesn't break Sudoku rules. And on the diagonals, oh, good effort on that diagonal. Right, those 9 digits must be different, for instance, because that's a marked diagonal. The same is true for the other one. Those are the rules, and bear in mind that title of Ready, Set, Go. If you've been watching our channel, you'll have some idea what I think Eric's hinting at, but if you don't, watch the video, see how it goes, and then you'll be able to attempt one of these soon. You probably are now. Do give it a go on the first link under the video. That's where you can find all the links to all our apps and SUDOKU PAD, etc., etc. I'm going to start now. Let's get cracking. Yeah, I mean, this is significant. So set is an abbreviation for set equivalence theory. Under which we know that there are various relations that apply to Sudoku grids. And we'll get into them when we need to, and if we need to. But I'm going to see what we can do first without. So this 10 cage, all the digits have to be different because it's in the same box. 1 plus 2 plus 3 plus 4 is the absolute minimum, and that is 10. And the 30 cage down here is the exact opposite. The maximum of 4 Sudoku digits adds up to 30. So we can fill in 9876. Now take 1 away from that and you get this 29 box. How can you take 1 away from 9876 without having a repeated digit? Only by taking it away from the 6 and coming up with 9875. And similarly, we add 1 to the 4 from the 10 cage and we get an 11 cage. So those digits must appear in those positions. And if you know the first example of set theory we got to see is what is called the Fistemafel ring. And I think we'd better explore what that is now, to be fair. I think we could make a little further progress without it, but I have a feeling this puzzle is set up to demonstrate it virtually. So what I'm going to do is highlight row 3, row 7, column 3 and column 7 in one colour. Well, in 2 colours. So if I make them all blue, now to take row 3 and row 7 means you're getting 2 sets of the digits 1 to 9. To take column 3 and column 7 means you're getting 2 sets of the digits 1 to 9. To take them both means you're getting 4 sets as long as you double count these purple cells So each blue once and each purple twice is 4 sets of the digits 1 to 9. Now another way of finding 4 sets of the digits 1 to 9 is by looking at the corner boxes, boxes 1, 3, 7 and 9. Again, by the rules, they must be 4 sets of the digits 1 to 9. And therefore, what we've got in blue, counting purple twice, and what we've got in green are exactly the same digits. That's clear. Now let's take out some of those digits that are counted once in blue and green, and we must still be left with the same digits in blue and green. And then if we take out these corner cells once from the purple to leave blue, and once from the green to leave no green, then we get these 2 sets of digits. And now we have 16 digits in green that are exactly the same digits as the 16 digits in blue on what has become known as the Pfister-Maffei ring, because it was Pfister-Maffei who introduced us to the concept. That's why. And therefore, the digits we have highlighted in green, and we know what those population of 16 digits are in this puzzle, they all appear in blue. Now, we don't know where they go yet, but this might be very helpful in determining how to solve the puzzle. Let's just check out these boxes as well. They're quite interesting. They're obviously 2 sets of the digits 1 to 9 because they're 9-cell cages, and the rule in the cage is that digits don't repeat, so it must be a full set. Now, if that's two sets of the digits 1 to 9, what have we got in these corners? We've got 1, 2, 3, 4, 6, 7, 8, 9, 5, 1, 2, 3, 5, 7, 8, 9. So we've got 2 sets of the digits except for the numbers 6 and 4. And these blue cells are therefore 2 sets of the digits 1 to 9 except for 6 and 4. And what does that mean? We're missing 1, 6 and 1, 4. Just trying to work out the relation. So those 4 cells must be these 2 plus a 6 and a 4. I think that is right. But I don't quite know what to do with that information. So let's add up these boxes. The secret, of course, that we're working on all the time is that every row, column and box adds up to exactly the same number because it always contains the digits 1 to 9. They add up to 45. That's the secret. But these 3 cages add up to 40. So you deduct that from 45 and these 2 add up to 5. That's either a 1-4 pair or a 2-3 pair. I don't know what the answer is yet, and I don't actually know how to solve this puzzle yet, but that's quite low. These have to be quite low to keep that down to a 9 at maximum. 14 there is either 9-5 or 6-8. If it was 6-8, this would be a 9-4 cage. If it was 5-9, this would be a 6-7 cage. So it's one or the other. And 9 must be used. That's probably not very interesting. I don't think I can tell what this central digit is yet, so I'm not quite... I mean, there's every chance, given this title, that we're meant to look at another set somewhere in this puzzle, but I can't work out what that one is yet, so I'm going to keep looking at this one example of set theory, the Pfister-Maffei ring that we've looked at so far. Just see if we can deduce what to do with that. These, for instance, we know what that population of 5 digits is. Maybe it is to do with the fact that those 2 include 6, 4 and whatever these 2 are, because of eliminating these 2 sets of the digits 1 to 9 against what we know is in the ring. I don't know how we're meant to achieve that particularly. I guess it means that the digits 6 and 4 are on these cells and not in the center. where we also know the digit 9 doesn't appear because that must be in one of these. Not that helpful as a guide. I think this one, I don't know, this one looks more helpful. If those add up to 9, say, what does that mean? Now, I don't know. I don't quite know how this works yet. Ah, here's a thought. Right. I hadn't thought of this before, but 14 and 13 is 27. So these other cells in the row add up to 45 minus 27 equals 18. Now, that plus these two cages, which are each 45, and therefore add up to 90, is 108. Plus these two cells and that one again is 126. So the blue area, counting the central cell twice, is 126. Now let's remove 45 being the central cell once from that count, and we are left with 81. And that means that the blue area, the Fistomephel ring, plus that equals 81. Well, we know the blue area is the same as the green areas. So let's add those up, subtract from 81, 30, and I guess 40 is 70, and 10 is 80. 81 minus 80 gives us the central cell. That's a 1. Okay, there we go. So there's no 1 on the rest of that diagonal. This pair that adds up to 5 now can't have a 1 in it. That must be 2, 3. That means this 9 cage must be 4, 5. The 13 cage must be 6, 7. The 18 cage has 8, 9 in it. None of that has violated these having to have a 6, 4 on. These can't have a 6 and 4 in, or they'd repeat in the central box. That 1 hasn't determined what these are yet, though. Right, let's... now, this arrow can't be 2 plus 3 plus 4, which is the only way you could not have a 1 on it and come to a Sudoku digit there. So there is a 1 on the arrow. The minimum it can add up to now, because of that cell, is 1, 2, 4. So that's 7. I liked the maths that got me the 1, but I feel it should have got me more digits than that, and it didn't. Oh, okay, yes, look, that's now a 2, 3, 4, 5 quad on the negative diagonal. So the other cells on the diagonal have to be 6, 7, 8, and 9. These two can't be 8 and 9 because they're used up in the central box in a pair. So they're 6, 7. Here we have 8, 9. Now, I can't do anything quite like that for this, or can I? Has that helped with this digit? Not properly. I should be able to work something out from here. Right, we've got 2, 3, 4, and 5. Where's 1 going to go on this diagonal? Oh no, 1's already on it. Sorry, that's a daft question. 6 and 7. One of these has to be a 4, doesn't it? Because I worked out that these 4 are 6 and 4 plus those 2. So those don't include a 4. Ooh, and these 5 have to add up to 18, don't they? Which is either, could be 1, 2, 3, 4, 8, 1, 2, 3, 5, 7, 1, 2, 4, 5, 6. Oh, well, no, they don't have to have a 4 and 6 on. No, they can't have a 4 and 6 on. I think that's the conclusion. These four are 4 and 6, and these two. So there must be a 7 on those two because of the 6-7 pair there. Wow, okay, that works. So a 7 there stops this being 6-7. So that's 4-9. This becomes 6-8. Now this group adds up to 1, 2, 3, 5, 7, which is 18. This is either 4 or 9. If it's a 4, that's a 1-3 pair, could be. I mean, there is every chance this is a very complicated way to go about solving this puzzle, but I'm very much encouraged to do so by the title, and I'm going to do it. This can't be an 8 because there's 6-8 in the box, so that's 7 or 9. Now, if it was a 7, we'd have 1, 2, 4 here, 3, 5 here. That would be a 3. That would be a 2. This would be 9, 5, 8. It does all work. Somehow it seems more likely to me that that's a 9, in which case this would either be 1, 3, 5. It couldn't be 1, 2, 6. So this is either 1, 3, 5 or 1, 2, 4. Forming, so it's using 1, and between them they're using 2 and 3, and 6, 7 there. So these cells are from 4, 5, 8 and 9. That one can't be 9. This one can't be 4, obviously. Still, I don't think that's quite giving me anything completely. Maybe I need to be considering this cage harder. Or is it still the Fistemafell ring? Should I be thinking about that? The 2-3 pair there. No, I don't know. I mean, I think this relationship between those 4 and those 2 is actually quite important. So whichever of 2, 3 and 5 goes in those cells is on that diagonal. Should I know what it is? I don't know. Every time I try and think about this whole population of green numbers, it doesn't really add anything to me about what I know about the blue ring at the moment. So I'm not too troubled about that. I think I'm going to have to work on the arrows a bit more. So this one is either 5 equals 4 plus 1, 8 equals 5 plus 3, or 9 equals any of those, and this could be 4 or 5 then, but it can't be 5, so this could be 4. Does that mean there's no way for this to be a 4? No, it could be if that's a 1. Okay, so I can't rule that out. So we get 1, 3 or 4 here. If 5 was on this diagonal, there's a problem, I think. No, there isn't. The other one could be 2, 3 or 4, as could those. No, that's not true. Okay, come on. I need to just focus a bit better now. That's either 1, 2, 4 or 1, 3, 5. If it's 1, 3, 5, we get 2, 4. I don't know. Okay, there's a 7 X-wing between these two boxes. That means that 7 is used up in those two boxes in row 1 and 2, and in row 3, 7 must be in this box in one of those two cells. I mean, that's not wildly helpful. I could probably do that. Oh yeah, 6 and 8 are here, 6 and 8 are here, so 6 must be in one of those two. Five there and 5 there, so 5's, but 5 could be in that cell as well, so that's not quite so clear cut. Gonna keep trying to do the same sort of thing. 9, 9, again 9 down here. And that's about it. I haven't got much more of that logic to use. Maybe I could rule out this being a 4. The 1, 3 there would put at least 2, 4 onto that arrow, for instance. No, it's not inherently impossible. Oh, it's probably the set theory again, isn't it? I need to do a little bit more thinking about that. 1, 2, 3, 4, 7. So 5 could be... Maybe if I could narrow this down more. Or maybe it's about how many 1s I need on the Fistemethel ring or something. That's a bit of an odd notion. If these can't be 1, there can only be 1, 1 on these 4 blue cells. I'm going to be putting 2 1s from these 2 corner cages onto the Fistemethel ring. No, that doesn't lead to anything. I need to get right, this 8-9 pair maybe. I need to get 2 8-9s on it. So if that was an 8, where would the 2 9s be? One would be there. The other couldn't be here, so it would have to be in this segment. Is that a way to look at it? No, not really, because I don't know that that's not a 9. But it looks harder. If that's an 8, the other 8, which couldn't be anywhere there because of the diagonal in this box, would have to be there. If that's an 8, this has to be an 8. That's quite strong, actually. If this has to be an 8, it's with 5, 3 up here. That feels better and more interesting. And if that's an 8, this is a 9. The other 9 has to be down in row 7. I don't know, that's not a problem as such. I do think this is the version that has the most pressure. Probably not going to be right that this is an 8, because it's so pressured to put a 5 there and a 3 there, to have nowhere else 8 can go in the blue. That's forced to be a 9. This gets forced to be a 7. That's interesting. So when that happens, if that's an 8 and therefore that's an 8, 9, 7, you get 1, 2, 4 here. 3, 6, 7, 8, 5, that becomes 9. 9, 5, 8 there. This has to be 4. I mean, it forces a lot of things. It would actually be very useful to make this an 8, because it would force so much up here. 9, 5, 8, 4. I can't quite see that it breaks anywhere, and that's what I need at the moment, is some reason to disambiguate either this 8, 9 or this 6, 7, or reduce 2, 3, 4, 5. Yeah, come on, think about it again. There's one thing I'm missing here. What is that? Maybe it is up in this box. These are from 5, 6, 8, and 9. These are from 5, 7, 8, 9. So that's a quadruple. And this can't be 6. I don't know that that's helpful. This 5, 7, 8, 9 quadruple. And if that's 8, then these are 9, 5, 7. That's a 6-8 pair, which is just what it wants to be. Ah, so if that was an 8, that became an 8. Oh yeah, no, that's what made this a 7. That puts a 6 there. That's interesting. There's meant to be 2 7s in the blue because there's clearly 2 7s in the green. Now if that's a 7, oh yeah, of course there's 1 7 in one of these 2 cells. So if that's a 7, it forces a 7 here. Yeah, I can't see that doesn't work for any reason. Maybe it is all about this. If it's a 9, is that a problem? Then we get 1 3 5 here. We definitely get 2 and 4 there. That puts 3 5 here. Makes this a 4 8 9 triple. What's the problem there? There isn't a problem. This is either 1 3 5 or 1 2 4. So it's a 1 2 3 5, 1 2 3 4 5 quad with this, whatever way round it works. So that's part of a 6 7 8 9. Quintuple was the 1 2 3 4 5. This is part of a 6 7 8 9 quad. That's 8 or 9, as are all of those. So one of those has to be 8 or 9. I suppose. No, I don't know that that's necessarily true. Oh yeah, they can't both be 6 7 because that would break. So it is true. So 8 and 9 are definitely used in this group. And 5 4 here. So these definitely include 1, 1 of 2 or 3, and 1 of 6 or 7. I just don't know quite how to use this. Maybe it's these 2 cells, which are from 2, 3, 5, and 7, and include a 7. Just a deduction away here. What is it? What am I missing? Is it very obvious? Maybe it's just Sudoku somewhere. I mean, this could easily be one of those points that people point out that we're off thinking about complex stuff and there's ordinary Sudoku to do, but I can't see how that's the case this time. This arrow just doesn't look very helpful at the moment. I don't see why there's much pressure on it. This one, on the other hand, maybe if it was a 9, which this couldn't be 4 5. Would have to use one of 1 2 or 3, or both if it's a 4. So these can't both be from 1 2 3. No, that's not true. That might only use one of 1 2 3. That could use 2 of them. That's nonsense. Right, maybe these cages. I've got 3 cells that are definitely from 6 7 8 9. Up here I've got those that are. I need a 4 in one of these groups. That's going to put a 4 into one of these groups. But actually both of those could have a 4. In fact, I think maybe both of them have to have a 4. Not sure about that. But I was just thinking that there isn't a 4 on this diagonal because there has to be a 4 on this bit of the diagonal. So those don't include 4s. Or, well, I don't know what else or. It wasn't as clean cut as this diagonal. Oh, 5 has to be in those cells because it can't be up there. So they're not 5s. 4 has to be in those two, so those don't have 4s. I mean, it's not very strong, is it? Nearly got a 1, 2, 3, 4 quad in this row. If that was a 4, because of this being a 5, then we'd have 4, 1 there, 3, 2 there. This would go 4, 1. This would be a 1. And this couldn't then be 1, 2, 4. Ah. So if that's a 4, or if that's a 4, that's a 4, and you can't have 4 on these cells. And if that's a 4, you can't even have a 4 there. So this being a 4, of course, stops this being a 7. 4, in fact, in either of those cells stops this being a 7, but especially that. So if this is a 5, that can't be a 7. That would have to be a 9. This would become an 8. This would become a 9. I think that's probably what does happen, but I cannot quite prove it now. Just trying to find a way to prove that. This is almost from 1, 2, 3, 4, but it could be a 5 if this was a 1, 5, 3, 9. If that was a 5, neither of these could be a 5. This would have to go 9, 8, 1. Ah, so if this is 1, 3, 5, that's 9, 8, and this is 1, which puts 1 there. That would force the 1 to be here. One, 3, 5 is actually very constrained here. So maybe that's what to think about. If this is 1, 3, 5, you get what do you get here? That's 1, 3, 5. This can't be 8, 5, 3 because that would clash with the 5. It can't be. It would have to be 9, 8 with a 1 there. That's what's right. Yeah, I just worked that out a moment ago. Why can't I keep that in my mind? 9, 8, 1 there. But wouldn't that be too many 9s? That would be too many 9s in the blue. This would be 1, 3, 5. That would be putting a 9 here. We'd have to put a 9 here. That 9 would force the 9 on this diagonal to be here. We'd have 3 9s in blue, and set theory tells me we're not allowed to because we've only got 2 green 9s. So that is not 1, 3, 5. We know it can't be 1, 2, 6. It must have a 1. It's 1, 2, 4. Here we go. That's a 7. That's a 7. This one isn't. This is now a 3 because of the 1, 2, 4 there. They also sort. Oh, well, they make this a 3, 5 pair that I haven't resolved. Now we need to have a 4 on the diagonal. That's now here. 1, 2, 4. We've got the 3, 5 pair. So this is a 2. This is 3 or 5. Now, how many 3s are we allowed on the diagonal? 2. Oh, this has become a 2. Right, we're getting somewhere now, surely. That's the same as that, obviously. Okay, that's fine. Now, 1, 2, 4. So we can take 4 out of those cells. This can't be a 5 anymore. That's part of an 8, 9 pair. So this is part of a 5, 7 pair now. That can't have a 5. This is a 6, 8, 9 triple. That is 2 or 6, checking the diagonal as well. This either goes 9, 8, 1 or 8, 5, 3, so that's not a 4 now. Okay, this is progress finally. Oh, that 7's made this a 6, clearly. It's very obvious when you spot it. 7 there. This is a 789 triple. This is now a 136 triple. Now I'm probably meant to be doing it by what's on the line. So we've got 2 7s. We can't have a third. That's not a 7. Now we've got 2 sets of 8 9. So we've used up all those high digits that are going to be here. We're going to have 1 6, 1 5, and then, oh, a second 5, of course, and all the 1 2 3 4s that are needed. So the 2 5s, now one of them has to be there and one of them has to be in these cells. But I think they both have to be in the 2 cages. Yes, let's look at the cage, of course. We've got a 6 in this cage, so that's a 2. We've got a 2 and a 4, so that's a 1. We need a 5 in the cage. These cages are very helpful if I would only think to look at them. So what about this cage? 8, 9, 2, 7 in it already. We need 1, 3, 4, 5, 6. That's 1, 3, or 6. These can't have a 6 in because of the 6 up there. And this can't be 1 or 4 on the diagonal. That is 3 or 5. I think that elimination is right. And that 3, 5 pair is going to sort out 5s up there. But also those can't be 3s. So that's a 1, 6 pair. This is where 4 goes in the cage. And that is right. That's all good. Okay, now that means this can't be a 6. It means this can't be a 5. This either adds up to 1, well, it either adds up to 3, 4, or 5. 1, 2, 1, 3, 2, 3, could be 1, 4. But anyway, we've got a 1, 2, 3, 4 quad in the column. Oh, this can't be 2, obviously. Yeah, I don't quite know what that adds up to yet. Those don't have a 1 in now. This is either 9, 8 or 8, 5. So it uses an 8 and that doesn't. 6, 8, 7, 4. Okay, what's going on here? 7, 4, 9, 5. Ooh, can that still let this be 3, 1? You get 6, 5, 2, 9, 8. Yes. How about a 9 there? This couldn't be 4, 5 or 7, 2. But it could be 8, 1 or 6, 3. Ah, okay, that's not resolved. Now something must have been. I'm just missing the effect of what we've done somewhere. This surely, oh, there must be a 6 in one of those two, so that's not a 6. 6, 7, 8, 9. 4 has to be in one of these 2 cells, and therefore in one of these 2, therefore in one of these 2, and that trail runs dry there. Oh, this is a 1, 2 pair in the column. That's all finished. Right, so that's not a 1. Ah, now these already add up to 7 or 8. That can't be 3. This can't be 7. I said at the beginning those could be 4s, both of them. Or I said they could be the same. And it looks like they might easily end up both being 4s. That is 3, 4, or 5. This is a triple here. We've got an 8, 9 pair. So these are from 1, 6, 7, but they can't include a 1. So that's a 6, 7 pair. We get the 1 here for the row. 3, 6 are there. Now, this is a 4, 8, 9 triple in the column. And that's 1, 3, or 6. Don't say that ends there as well. No, 1, 3 can't be here. So they are both up here. So the 6 has to be here. Actually, that 1 proved it in the cage. Not good at using these particular cage shapes, maybe because I've covered them in blue. Right, this now can't be 6, 3, 7, 2 or 4, 5. So it's either 1, 8 or 1, 3. Definitely uses a 1. And that's very interesting because that makes this a 2. So now this has to be 3. They're not repeated after all. Now we get 5 and 3 on the diagonal. And in the box, this is a 4. Now that 5 fixes 3 and 5 there as well. I have a feeling they've been available for a while. 7, 3, 4, 2, 6, 8. 9 in this box is instant now if one just knew to ask that question. That can't be 7 or 9. In fact, there's no 9 in this cage because we've already got it. So there must be a 9 on that diagonal and not in those cells. I suspect I'm overcomplicating everything now. That's a 4-6 pair. Those can't have a 3, so they're 1 and 8 adding up to 9, and that's going to be a very helpful arrow in dealing with these columns, I think. 9, 1, 8, that's a 2-3 pair. The 9 we got on the left has made that 8 and 9. Right. So now it's just the top. Now this, has this not been sorted out yet? Really hasn't. 6, 1, 7, 8, 9. No, the diagonal's not done. Oh, why can't I work out what to do next? It should be very clear from here, shouldn't it? 7. These 8, 9s, do they all work together? Oh, 7 can't be in those cells, but this diagonal needs a 7 on it in one of those positions. That's not extra helpful. 5, 7, 8. That can't be a 9. Still can't see what to do here. 5, 6, 7, 8, 9 quad. That's not doing anything. 5, 8 pair there. Wow. That took a while. Right. 7, 6, 7. We get a 6 there. Then we've got a 5, 8 pair still. 9, 8 on the diagonal. 9, 8. And the whole Fistemafel ring is done. 9 there gives us 8 and 1. That makes that a 5. This is now 8 and 9. 6, 8 on the diagonal. So 7 there. This 1, 8 is resolved. Yeah, this must be coming now. We know what this is. That's a 5. This is a 3. That means they can't be 3, and these can't be 1. So we know where 1 is in this green cage. 5 has to be on this diagonal, so it's there. That's not 1, so we know where 1 is in this one. 2, 3 pair there. Right, that's going to sort out a couple of the pairs. This is a very clever puzzle, isn't it? It really is, the way it all falls together at this point only. 4 there, 2, 3. On the diagonal, 2 and 4 fixes the other end, 3 and 2. So all the green and blue cells are all fully done now. I think we're just finishing off finally after quite a struggle. 7, 9, 4, 2, 1 pair left, 3 and 2. What a lovely idea. That's really well done by Eric. Very enjoyable puzzle. 44 minutes, my goodness, that's been longer than I expected, but very rewarding, very clever puzzle. Hope you enjoyed it. Hope to see you soon on the channel. Bye for now.